Welcome to this, our final lecture on natural convection. In the previous class, we had defined the scaled equations for natural convection, the equation for the temperature field, the mass conservation, divergence of velocity is equal to 0, and the momentum conservation in both the x and y direction. Okay. These equations, the diffusion terms in both the temperature and the momentum equation, had a factor of 1 over Grashof number to the half in them. And I told you that in most practical applications, the Grashof number is actually very large. And due to that, if you assume limit of infinite Grashof number and just neglect the diffusion terms, the result you get is that the convection, the temperature is a constant along velocity streamlines. That obviously does not satisfy the condition that the temperature has to be a different value at the surface of the object in comparison to the ambient, because the streamlines will go all the way from minus infinity to plus infinity around the object. So, for that we have to postulate the presence of a thin boundary layer near the surface. The thickness of that boundary layer decreases to 0 as the Grashof number goes to infinity in such a way that the solution of the equation, the equations themselves and their solution are independent of Grashof number in the limit as Grashof number goes to infinity. The streamwise distance and velocity can still be scaled by the characteristic dimension and the characteristic convection velocity around the object. The cross stream distance is much smaller than the dimension of the object. Therefore, we had defined a scale distance delta here such that y plus is equal to delta times, y star is equal to delta times y plus, so that y star is order delta and y plus is order 1 within this boundary layer. Y plus is the eta that I had in my previous lectures. Okay. So, y star by delta is basically y plus. In the mass conservation equation, for the derivatives of the x velocity and the y velocity to be of equal magnitude, okay, the x velocity scales as capital U, the convection velocity, x distance scales as L, y distance scales as delta. Therefore, the y velocity has to scale as delta times u for the two terms to be of equal magnitude. Okay. So, therefore, I had to define ui star is equal to delta times ui plus, and I put that into the equations and simplified. Okay. In this case, the mass conservation equation remains as it is. Okay. In the x momentum conservation equation, okay, what you got was a 1 over Grashof number per half delta square, because it has two derivatives with respect to y, the cross stream momentum diffusion. Okay. And in this case, since the thickness of the boundary layer is small, cross stream diffusion is much larger than the streamwise diffusion. Okay. The momentum equation perpendicular to the surface in the cross stream direction just reduced to the pressure gradient in that direction is equal to 0, because the cross stream velocity was very small, okay, whereas the distance is also small. So, the pressure gradient is large, okay, and if you do not have anything else in the equation to balance it, the equation for the flow in the boundary layer just reduces to pressure gradient equal to 0. Okay. And once again, in the energy balance equation, the convection term is balanced by the diffusion term, where I have a delta square, okay, due to the two derivatives and 1 over Grashof number to the half, okay, times Prandtl number. Obviously, if the equations have to be independent of Grashof number in the limit as Grashof number goes to infinity, I have to scale delta as Grashof number to the minus 1/4. Okay. And once you do that, both of these terms will disappear. Okay. Once you do that, both of these terms will disappear, and the resulting equations that I get are independent of Grashof number in the limit as Grashof number goes to infinity. Okay. So, this gives me the boundary layer thickness. Okay. So, this gives me the boundary layer thickness. Okay. The resulting equations are only dependent on the Prandtl number, and therefore, I can quite easily get the form of the heat flux. Okay. The heat flux goes as k into T partial T by partial y. I scale it by T naught minus T infinity and L, okay, and I get minus k into T naught minus T infinity by L. the characteristic dimension in the cross stream direction is not L itself, but rather L times delta, because delta is the dimensionless boundary layer thickness. Okay. So, this becomes my equation. Okay. I have to take the flux at y is equal to 0 at the location of the object, okay, integrate it over the surface of the object to get an average flux, okay, integrate over the surface and divide by surface area to get an average flux. Okay. That is a numerical exercise that I did not do, but I told you what the result is going to be up to a multiplicative constant. Okay. Up to a multiplicative constant, which is the Prandtl number in this case. The flux is going to be of the form a constant which depends on Prandtl number times k T naught t minus T infinity by L times delta, where delta now is Grashof number to the minus 1/4 power. Okay. So, if I define the Nusselt number as the heat flux, average flux divided by k into T naught minus T infinity by L, okay, it just becomes equal to some constant which depends on the Prandtl number times the Grashof number to the 1/4 power. Okay. We do not yet know what that constant is. It turns out we have to solve these equations in order to determine what is that constant. Okay. However, we can get some more insight by considering the limits of high Prandtl number and low Prandtl number. Okay. Recall that the Prandtl number is equal to nu by alpha, the ratio of momentum diffusion and thermal diffusion. Okay. Low Prandtl number will, for example, correspond to liquid metals where the thermal diffusion is extremely fast. Okay. So, the thermal diffusion coefficient is extremely large, that would correspond to a low Prandtl number limit. High Prandtl number limit will correspond to cases where thermal diffusion is slow, okay, organic liquids for example. Okay. So, we can look at what is the form of this equation in the limits where the Prandtl number is high and the Prandtl number is low. Okay. So, first we will consider the case where the Prandtl number is much smaller than 1. What does that physically correspond to? Okay. At the surface, I told you that I had a boundary layer thickness delta. Okay. Prandtl number is the ratio of momentum to thermal diffusion, okay, momentum to thermal diffusion. When the Prandtl number is small, the momentum diffusion is much smaller than the thermal diffusion. Right? That means that the momentum diffusion is going to be restricted to a thin region. Okay? The boundary layer thickness for momentum diffusion is going to be equal to much smaller than the boundary layer thickness for thermal diffusion. Okay. So, that is what is meant by low Prandtl number limit. Thermal diffusion occurs over a much larger distance than momentum diffusion, okay, because thermal diffusion is very fast compared to momentum diffusion in the limit of low Prandtl number. Okay. In that case, you would expect, for example, as you go away from the surface, the temperature field will decay over a distance comparable to the thermal boundary layer thickness, okay, whereas the velocity field will decay over a much smaller distance. Okay. The velocity field will decay over a much smaller distance, whereas the temperature field will decay over a distance that is comparable to the boundary layer thickness. Okay. Okay. Whereas the velocity field, the viscous effects are important only within a much smaller thermal momentum boundary layer. Okay. So, in that case, what would you expect? We need to find out what is the temperature, the heat flux at the surface. Okay. So, we need to know what is basically the slope of this temperature field at the surface itself. Okay. The slope for this temperature field is determined from the thermal temperature equation. Okay. That temperature equation has the form Ux partial T by partial x plus Uy plus partial T by partial y 1 by Prandtl number partial square T by partial y plus square. Okay. Now, I said that the thermal boundary layer and the momentum boundary layer are different. Okay. Now, obviously, the thermal boundary layer is going to be much larger than the momentum boundary layer in the limit as the Peclet number goes to 0. Okay. Therefore, I can define, okay, and let me look at the momentum balance equation Ux Okay. So, that is the thermal boundary layer equation. Okay. Now, I require that in the limit as the Prandtl number goes to 0, there still should be a balance between diffusion and convection within the thermal boundary layer. Okay. Thermal boundary layer is much larger in thickness than the momentum boundary layer. That means, in the momentum boundary layer itself, okay, convection and diffusion are of equal magnitude. Thermal boundary layer is much larger than the momentum boundary layer. That means that in the thermal boundary layer, diffusion of momentum is not going to be important. Okay. Diffusion of momentum is not going to be important. Okay. So, therefore, in order to, I have to rescale my coordinate by the thermal boundary layer, okay, thickness. Okay. So, I go back to my original coordinate. Okay. And I rescale y star is equal to a thermal boundary layer thickness, okay, a thermal boundary layer thickness times y, okay, double dagger. Okay. I rescale it as a thermal boundary layer thickness times y double dagger. Okay. I have to rescale uy star also as the thermal boundary layer times the same thing. The reason is because in the mass conservation equation, partial ux by partial x has to be the same as partial uy by partial y. Okay. And if I do that, you can very easily see that ux partial t by partial x will be equal to, okay, into 1 by delta thermal square partial square t. Okay. And I can do the same thing for the momentum equation. In that case, for the momentum equation, I will get so that is what I will get for the momentum equation. Now, here in the thermal equation, in the equation for the temperature field, I require that convection and diffusion have to be of equal magnitude, okay, within this thermal boundary layer. And what that means is that the thermal boundary layer thickness delta T, okay, is equal to Grashof number to the minus 1/4 Prandtl number to the minus half. Okay. That is the thermal boundary layer thickness. Okay. And if I use that thermal boundary layer thickness, then this equation, okay, the energy equation just reduces to, okay, the energy equation just reduces to ux partial t by partial x plus, okay, is equal to partial square T star by, that is what it reduces to. And the momentum equation, okay, if I use this definition for the boundary layer thickness, I will get okay, delta T goes as gr power minus half minus 1/4 pr power minus half. Okay. So, if I divide throughout by that, what I am going to get is a factor of the Prandtl number here. Okay. We are considering the limit where the Prandtl number is small compared to 1. That means that in the momentum equation, right, this diffusion term is small compared to the convection term, the pressure gradient and the body force. That is anticipated. The momentum boundary layer thickness is very small compared to the thermal boundary layer thickness. Viscous and inertial forces are of equal magnitude in the momentum boundary layer. Therefore, if I come out to the thermal boundary layer, there the viscous forces for the momentum will not be important. Okay. So, that is what the equation is reduced to in the limit where the Prandtl number is very small. What is important for our calculation is basically that the thermal boundary layer thickness goes as gr power minus 1/4 Prandtl number per minus half. Okay. And we know from the previous calculation, okay, that we know from the previous calculation that the Nusselt number has to go as, in this case, some constant divided by the scaled boundary layer thickness. When the Prandtl number we had not specified, that constant was just a function of the Prandtl number. In this case, we know what functionality of the Prandtl number it is. Okay. And this will straight away tell us that the Nusselt number has to be equal to some constant. Okay. Okay. I will call it as for high Prandtl number, I am sorry, some constant C1 in the limit of high Prandtl number times Grashof number to the 1/4 times Prandtl number to the plus half. Okay. So, that is what the correlation should be in the limit where the Prandtl number is small. Okay. The Nusselt number is proportional to some constant, okay, times, okay, this constant C. Now, this is a universal constant. It depends only upon the configuration. It does not depend on the Prandtl number. That times the Grashof number to the 1/4 power times the Prandtl number to the half power. So, that is what this correlation for the Nusselt number should be in the limit when the Prandtl number is very small, or when momentum diffusion is much smaller than thermal diffusion. Now, what about the case when the Prandtl number is large? Okay, that is when the Prandtl number is much greater than 1. In this case, you would expect momentum diffusion to be much faster than thermal diffusion. Okay. If you go back and look at the boundary layer again, since momentum diffusion is much faster than thermal diffusion, okay, as a function of the distance from the surface, you would expect the temperature field to decay very fast. And the thermal boundary layer thickness would look something like this. Whereas momentum diffuses much faster, so it goes out to a much larger extent. And the velocity field you would expect should go something like that. The momentum boundary layer thickness is much larger. And the momentum boundary layer thickness will look something like that. Our estimate for the velocity was this velocity, the maximum velocity, based upon a balance between the body force and the inertial terms in the momentum conservation equation. this velocity within the thermal boundary layer may not be as large as the maximum velocity, because the thermal boundary layer thickness is much smaller than the momentum boundary layer thickness. Therefore, within the thermal boundary layer, we would expect the velocity to be smaller than the velocity that is predicted on the basis of a macroscopic balance. Okay. Therefore, I need to rescale the streamwise velocity within the thermal boundary layer by this velocity. I do not yet know what that is. All I know is as the Peclet number becomes larger and larger, this relative boundary layer thickness should become smaller and smaller. Therefore, the velocity within the thermal boundary layer for the mean flow should become smaller and smaller. Therefore, I can postulate that within the boundary layer, okay, the velocity, the velocity, okay, which I have scaled, okay, will go as Peclet number to the sum power, okay, at the negative power, so that it is much smaller than the momentum boundary layer thickness in the limit as the Peclet number becomes large. Okay. Therefore, I should be able to define a scaled velocity, okay, Peclet number to the minus a times ux. Okay. This scaled velocity is now order 1 within the thermal boundary layer. I do not yet know what this power a is, but I will determine that from the balance equations. Okay. So, the original balance equations, okay, which I had were of the form, the thermal balance equation was ux partial t by partial x plus is equal to thermal boundary layer thickness partial square t by partial y square, okay, or expressed in terms of the scaled coordinates. Expressed in terms of the scaled coordinates, what I had got was that ux is equal to 1 by Prandtl number Grashof number to the half. Okay. Here I have neglected streamwise diffusion in comparison to cross stream diffusion, because I expect the boundary layer thickness to be much smaller than the characteristic size of the object L. Okay. Now, I make this substitution, ux star is equal to p power minus a into ux double dagger. I expect this to be order 1. In addition, I have to write y star is equal to some boundary layer thickness times, okay, where delta t is a boundary layer thickness, okay, for the thermal boundary layer. Okay. Now, from the mass conservation equation, I know that, okay, uy star, okay, will be equal to, okay, 1 will be equal to delta t, right, times p power minus a uy double dagger. The reason is because from the mass conservation equation I require that ux by partial x plus partial uy by partial y has to be equal to 0. Therefore, partial ux by partial x and partial uy by partial y have both got to be of equal magnitude. Okay. If I insert that into this equation, what I will get is Peclet number power minus a into is equal to 1 by Prandtl number Grashof number to the half. I have a factor of L by delta t here whole square, okay, because the original scaling for y was in terms of L. Okay. Okay, so therefore, I should write y star is equal to delta t by L if L is a boundary layer thickness base, which is a dimensional boundary layer thickness. Okay. Wait. Okay. So, that is the equation. Okay. And from this I know what is for the balance between the convection terms and the diffusion terms, these two have to be of the same magnitude for the convection and diffusion terms to be of equal magnitude, because all the other terms are all scaled. They are scaled so that they are order 1. Okay. So, on this basis I can get one condition. I get that delta t by L the whole square is equal to PR per A minus 1 GR per minus half. Just by balancing these two, because I know that PR per minus A is equal to delta t by L the whole square 1 by I am sorry. L by delta t whole square. That is, if I balance these two, L by delta t the whole square into 1 by PR GR per half. I take it to the other side, and I will get this relationship. One relationship between delta t by the L the whole square, the Prandtl number, and the Grashof number. Second relationship from the momentum conservation equation. In this case, the momentum conservation equation within the thermal boundary layer. The momentum boundary layer is much larger than the thermal boundary layer. Within the momentum boundary layer, viscous and inertial effects are of equal magnitude in the momentum boundary layer. The thermal boundary layer is much smaller. So, within the thermal boundary layer, momentum diffusion is going to be much faster than convection, because as I reduce the thickness, diffusive effects become large. You recall the Reynolds number has a length scale in the numerator, ratio of inertial and viscous effects. As the length scale decreases, viscous effects become larger than inertial effects. In this case, in the momentum boundary layer, over a thickness delta m, inertial and viscous effects are of equal magnitude. When the thickness becomes much smaller than delta m, you would expect viscous effects to be much larger than inertial effects. So, in the momentum equation, the streamwise momentum equation, the inertial effects should be negligible, and there should be a balance between the pressure gradient and the viscous effects. In dimensionless form, this was written as partial P dynamic pressure by partial x plus 1 by Grashof number per half. Once again, retaining only the cross stream diffusion of momentum, neglecting the streamwise diffusion of momentum. Partial square ux star by partial y star square. Now, I express ux star and y star in terms of this velocity, scaled velocity, because I know it has to be much smaller than the velocity in the momentum boundary layer, as well as this thickness. So, 0 will be equal to, there should be a negative sign, my apologies. I have PR per minus A divided by GR per half, partial square ux. And I should also have a factor of L by delta t the whole square, because the boundary layer thickness is scaled by L by delta t. I have to scale the velocity differently within the boundary layer thickness. And for the two terms in the momentum conservation equation to be of the same magnitude, I require that this whole thing be of order 1. I get a second condition for the thermal boundary layer thickness. So, the second condition is that delta t by L the whole square is equal to PR per minus A into GR per minus half. This is required for the viscous and the pressure gradient to be of equal magnitude within the momentum boundary layer. Okay. So, this gives us two conditions. Okay. This gives us two conditions. Both of these have to be the same if the boundary layer thickness predicted is a common one. It is for both equations. In both cases, the boundary layer thickness has to be the same, the thermal boundary layer thickness. Okay. So, therefore, I require that PR per A minus 1 GR per half is equal to PR per minus A GR per minus half. Okay. The Grashof number will cancel and I will get that A will be equal to 1 by 2. Okay. A will be equal to 1 by 2. Okay. With that, the boundary layer thickness whole square is equal to PR power minus A, Prandtl number per minus half, Grashof number per minus half. Okay. Which means that delta T by L is equal to Prandtl per minus 1 by 4, Grashof per minus 1 by 4. Okay. So, that is the boundary layer thickness. Okay. The boundary layer thickness in the case of Prandtl number much larger than 1 is Prandtl number per minus 1/4, Grashof number per minus 1/4. Okay. In the previous case for Prandtl number much smaller than 1, it was Prandtl number per minus half into Grashof number per minus 1/4. And from this we know that the Nusselt number has to scale as the inverse of the boundary layer thickness, because the gradient is the temperature difference divided by the boundary layer thickness. It scales as the temperature difference divided by the boundary layer thickness. Therefore, the Nusselt number now is proportional to 1 over delta T, okay, which is basically equal to some constant times Prandtl number per plus 1/4, Grashof number per plus 1/4. Okay. So, that gives us the dependence, individual dependence on the Grashof number and the Prandtl number in the limit as the Prandtl number becomes much larger than 1 or the thermal boundary layer thickness is much smaller than the momentum boundary layer thickness. So, finally, these are the relations we have for natural convection. General relation, Grashof number per plus 1/4, that is because the boundary layer thickness goes as Grashof number per minus 1/4. Okay. Grashof number is the square of a Reynolds number based upon the convection velocity due to the body forces. In the limits where the Prandtl number is much larger than 1 or the Prandtl number is much smaller than 1, we can get relations. Okay. The scalings, Prandtl number per 1/4 and Grashof number per 1/4 for the case of high Prandtl number per half times Grashof number per 1/4 for the low Prandtl number. These are universal. Okay. These are universal scalings. Okay. So, if I write this in terms of the proportionality, okay, this is always true. Okay. The constant in the equation does of course depend upon configuration, whether you have a flat plate, a tube, a sphere, all of those things. That will depend, the constant will depend on that. The scaling in terms of the Prandtl number and the Grashof number does not depend on the specific configuration, it is universal. In general, it is some function of Prandtl number times Grashof number per 1/4 for Grashof number much larger than 1. I had shown you that this is usually the case. The Grashof number is usually much larger than 1 in most applications. Limiting to restricting to limiting cases, when the Prandtl number is much larger than 1, you get a 1/4 power on the Prandtl number, 1/4 power on the Grashof number. When it is small, it is Prandtl number to the half, Grashof number to 1/4. And as promised earlier, I have shown you how to derive these equations just by scaling the mass, momentum and energy conservation equations alone. Just from that scaling and the boundary layer thickness that yields when we scale the different terms in the conservation equation, we were able to derive these. You can do analysis in this case, but that would require some knowledge of fluid mechanics. Okay. Therefore, I have not gone through that. I have shown you how to get these relations without having to go through a detailed analysis. The constants of course can be determined either from experiments or from simulations or from a more detailed analysis of the velocity fields. This completes our discussion of natural convection, how the Nusselt number or the heat flux scales with the dimensionless parameters, the Grashof number and the Prandtl number. So, this completes our lesson on natural convection. Thank you.